Good morning. My name is Panevsky. I manage the Avionics lab at the Aerospace Corporation. And I'll be talking today about how we designed and built rapid prototyping hardware-in-the-loop system using commercial hardware and lots of FPGAs. So a little bit of background. What we do at the Avionics lab at Aerospace, our mission there is to perform test like you fly simulations of various space vehicles. And the idea there is that we want to do IV&V on the flight computer and on the flight software that's running on it in a realistic environment. So what that means is we want to run the flight code of the contractor on their actual hardware, run their actual binary with no modifications, and then be able to perform a complete mission, which means output telemetry, do all the dynamics, inject errors, create anomalous conditions. So basically, the objective is to try very hard to break the flight code and in a realistic way and find out if the flight code can handle it. So the way we used to do things is people would usually wait until a new flight computer is basically done, and the flight code is usually also done. And then we would go and build a hardware-in-the-loop system that is essentially a laboratory version of the flight computer with all kinds of I/O so that we have full visibility into it, and then we run the flight code. But what that meant was that we had to wait until the flight computer that we're targeting is basically a frozen design, because the Hill systems that we were able to build before were custom and very expensive, very difficult to integrate and to debug, so you can only do it once, which means you had to wait until everything was pretty much done on the other side before you can start. So we wanted to change that paradigm. We wanted to be able to build a system essentially in parallel with the contractors. And as they're developing and changing it, we can do our IV&V in parallel. And so we wanted to find out a platform, a paradigm that will allow us to do that. And so what we've done is on that picture on the right side, you see one of our legacy hardware-in-the-loop systems. It represents essentially it's the flight computer of an existing system, and it's the lab version of the flight computer. And you can see that it's fairly, I mean, it's all custom. So it's very difficult to debug and even more difficult to integrate and to get it to work. And once you get it to work, you don't want to change anything because, again, it's very difficult to debug. On the left side, you see what we built recently, which is our new Hill systems that uses lots of COTS technology and a few custom boards, but they're also flexible because the custom boards have FPGAs on them. And also the COTS technology that's in the background is also very heavy FPGA-based. So, and there's no, I mean, real mystery of what we've done here is the chassis that you're sitting there in the background is a Pixie chassis from National Instruments. And lots of the FPGAs that are inside the chassis are just COTS FPGA LabVIEW boards. So the glue that binds the whole system together is the LabVIEW environment, which allows us to have this model-based development. And of course, it has FPGA extensions, so we can design the algorithms in this LabVIEW paradigm. And then one of the things that the LabVIEW does for you is it does code generation. So in the case of an FPGA, it creates the LabVIEW talks to the tool chain of Xilinx in this case, which creates the VHDL, although they don't show you the VHDL. And then at the end, you get the bit file, and you load it on your FPGA. So what the system basically looks like, and this is a working system. It took only about 6 months since we started purchasing hardware to integrate and debug and have a system that actually can run a complete full space mission right now. So what you're seeing on here is a sanitized version of the Hill. And on the bottom, these 4 boards are the only custom piece in the system, and they're custom because they contain the actual CPUs of the target flight computer, and those are not non-standard CPUs, so we can't really buy those. We have to build them, so we did. But they're flexible boards because they have FPGAs on them. Then they talk to commercial FPGA boards that are doing all of the I/O based on the contractor spec. And then the whole system is managed by, on top there is a real-time controller, which is basically running the Pixie backplane. It's running real-time LabVIEW, which gives us some time determinism. Actually, based on the talk so far, it doesn't really, I guess the correct expression would be, gives us, we don't overrun we do not overrun the frames. So that's what it is. When something runs, we don't exactly know at what nanosecond it's running, but we know that we'll run it at least as fast as we need to. So that's the Pixie controller. And then to close the loop, to run a mission of a launch vehicle or a spacecraft, you need also the dynamics, the physics side of that. So the workstation, there's no pointer here, but I think you see what I'm talking about. It's right up there on the northeast corner of the chart. It's a dynamics workstation. Okay. Okay, thank you. This dynamics workstation contains all the dynamics of whatever we're simulating, launch vehicle, spacecraft, and it's talking in a closed loop to the flight computer. So basically what we're doing is the dynamics is sending sensor data to the flight computer. Flight computer is then processing that, going through its integration loops, makes a decision, issues commands to what it thinks is the vehicle through communication bus. In this case, it's a 1553 somewhere in the diagram. The commands go to the dynamics. The dynamics responds appropriately. That closes the loop, and so you can run the entire mission. In the case of launch vehicle, you run for thousands of seconds. In the case of a spacecraft, you can run for months or longer. So the way we've done the firmware on the FPGA, this is sort of a chart for the firmware design. All I'm trying to point out here is that it's modular. A lot of when you build hills, you discover, once you build 2 or 3 of them, you discover that they pretty much all do the same thing. A lot of the functions that you need are they just, you see them over and over again. So there is no reason to reinvent the wheel every time. So what we've done is this modular design where we can reuse some of these pieces on later missions, on later programs, which we already are. And also, the modular design allowed us to have several people working on it at the same time. Now, the way these high-level tools work, typically, what we've discovered the best way to run it is we have an algorithm that some I/O algorithm from a specification document. So we're trying to encode that into the FPGA. Now, one thing that's really very useful when you deal with LabVIEW is that the people that you hire coming out of school, they usually know LabVIEW. They might not be very good programmers, but they know LabVIEW, and they know their subject matter. So instead of talking to somebody who's an FPGA or VHDL expert and trying to explain to them what we're trying to accomplish here, we can just plug in that guy right out of school and say, just do this in LabVIEW. And then then the tool will take care of the VHDL generation. So that's this piece here. Usually there is legacy code that people, for various reasons, don't want to rewrite. And LabVIEW has a way to plug that in. And then once that it's all nicely bundled, then you push a button and you get an error, typically. But eventually, you don't get an error. And that's what happens for the first 3 months. But eventually, you don't get an error. You get a bit file, which you deploy on your FPGA. And now you have a working system. And then you start integrating, and you close the loop, and you go back, and you have to change things and until it's all working and there are no more error codes in the system, and that's where we are right now. And one of the ways we've been able to do this debugging successfully is, well, before I get to that, let me talk about what we can do as far as ASIC emulation. The reason I'm saying ASIC emulation is because in the real flight computer, this entire I/O functionality is done on an ASIC. So basically what we're doing is the CPU is a separate beast. The CPU is the CPU. We're using the actual CPU. This way we can actually run the binary code. But it's the I/O chip in the flight computer is where it's all really happening. This is where if you have any problems, they probably will be there. So that ASIC chip is the one we're doing in the FPGA based on specifications documents. So having that ASIC emulated in the FPGA allows us to do all kinds of things. It allows us to have full visibility into what the chip is doing. It allows us to inject errors, allows us to stress the timing, and there are some more esoteric applications later on that we can think of. For instance, parts obsolescence at some point. The parts that are right now on the flight computer will not be available, but the FPGAs will still be available. And all you have to do is just put it on a red hard FPGA. I already showed you this chart, but I haven't shown you these red squares here. And that's part of the magic that allowed us to do the debugging so fast. And what we've done here, we essentially built in our own logic analyzer inside the FPGA. So anybody that used the logic analyzer knows that you can only capture, well, if you have lots of money, you can only capture a few seconds worth of runtime. And if you have a mission that's 20,000 seconds and you have some glitch that only happens once and you don't know where it happened, there is absolutely no way you can see it. So what we wanted to do was be able to essentially record the entire mission. So these guys are recording every single heartbeat of the FPGA, and the FPGA is essentially running at the same clock speed as the CPU. So everything that's happening in the system is being ported here through fast Ethernet, and then to a large RAID, very fast RAID unit is what we'll be using. And And then you have to go and unpack a gigantic file of gigabytes. I'm not sure how many gigabytes, but well, anyway, that's a different problem. But we're dealing with this right now. We're just generating this giant file that has everything in the system, and we are actually debugging that piece right now. This one is a sanitized chart that shows an early success story for this data logger tool that I'm talking about. It's there is some FIFO in the system that should never be full, and if it's full, it means that you're overrunning your frame, and it only happened once, and we caught it. And then with this data logger tool, what we can do is go in the neighborhood of where the glitch occurred and find out what the rest of the system is doing that led to this. And we cannot do this with a logic analyzer. You can't do this with anything else, actually. So this is what I'm talking about. We can do, we can capture rare events. We can post-process the data. We have to post-process the data. And then once you have the data in a nice format, then you can use your standard tools in Python, MATLAB, to analyze, to create predictive models of how the system fails, when it will fail, how you need to stress it so it doesn't fail or it fails, things like that. What we are working on right now, besides the data logger, is something that I find fascinating. Might work, might not, but we're going to do it anyway because I think it's fascinating. We've been told multiple times for these 3 days that going to safe mode is not a good idea, and I tend to agree. And also looking at various programs that we're working on at Aerospace, we see that the software is becoming so complex that there is no possible way that the designers can anticipate everything that can go wrong with the system. So what we want to explore is some elements of a neural network. AI is a fancy name for that, but it's really a neural network that we can maybe use for fault detection and management. And that's a tall order. So what we're going to try to do first is we'll go easy. We'll just use a GPU, which is easy to program, and create that system there first. And then if it works, we're going to try to port that to an FPGA, which is the FPGA sort of like a GPU because you have parallelism, but the FPGA is lower power compared to a GPU. So that's what's coming next. So in summary, what we've done is we've successfully, I think, changed the paradigm of many, many years at Aerospace of the way people were building hills and designing them, debugging them, and using them. And last year, we were just starting this, and we had another prototype development, which was sort of a hybrid system between this new approach and legacy. This is the new full-blown modern COTS FPGA-based system. And then already based on that, we are branching into some new hills that we're working on right now. So that's all I have.
Very good. Are there questions? Hold on. Go out for a
Hello. Hi, I'm Larry Ellis from Lockheed. With FPGAs, you don't have much flexibility, though, do you? Don't you have to respin them when you find out new things about how the spacecraft works or the launch vehicle or anything?
Respin meaning reprogram?
Yes.
Yes.
Does that cause you a lot of rework issues doing that?
The actual reprogramming is very quick. It takes a few minutes. If you have a bit file that works, You're talking about generating a new bit file.
Yeah, it seems like in my line of business, when we have to respin an FPGA, it seems to be weeks and months. Now, there are flight ones that go on flight boards, but that's different, I suppose. But
well, most of the time is spent in developing the code and debugging it. The actual once you have a good system and you can generate the code, it takes.
Okay, so you're flexible to changes
2
and
hours,
interrupts in
maybe?
the system to change things,
Right.
and okay.
The system right now, the LabVIEW takes about 2 hours to generate the bit file, which is not great, but we can live with that.
So I found your last slide about use of artificial neural networks for fault management interesting, but from what I have read, they are best used for matching patterns they've seen before. So are you working on developing a catalog of known fault scenarios, or where are you in the research is my real question.
We're working on trying to figure out what exactly, as a proof of concept, we want to. We're leaning towards using the AI as a sort of, for instance, in the case of a spacecraft, you have the hardware. If it fails, it fails. But sometimes you have what's called, graceful degradation, right? So it's sort of working, but not exactly up to spec. And the software gets upset about these things. So if you have a system that can detect that it's the pattern is sort of what you expect, let's say from a gyro or something, but it's not quite there, it can tweak it and filter it to what it needs to be so the flight code is happy. Something like that is, I think, doable as a first step.
Thank you.
Other questions?
Could you expand a little bit on your approach to data reduction and analysis for the very large traffic files, internal captures that you're doing?
Yeah, the files are really, even right now at this early stage, the files are already big, and they're going to be really big. So MATLAB is probably out of the question. It will crash, we think, although MATLAB has ways of loading data directly from file without loading the entire file. That's very useful. But what we're working on for real is on Python, which has the ability to, they have toolboxes that have the ability to load really gigantic data files and without crashing. So that's kind of what we're thinking about. That's what we're doing.
Is there a quantifier on really big?
Hundreds of gigabytes. That's for a launch vehicle. For a spacecraft, it would be, well, for a spacecraft, probably there is no reason to record the entire mission. You could, but I don't know why you would want to.
Other questions?